Hello, everyone, and welcome back. In our last session, we explored discrete probability distributions, like the binomial distribution. Today, we're shifting our focus to a new, incredibly important type of distribution. We'll be diving into the normal distribution. By the end of today's class, you will be able to describe the key properties of the normal distribution and understand the parameters that define it. You'll also be able to apply the empirical rule to estimate probabilities. Let's write those objectives down. First, we'll describe the properties of the normal distribution. Second, we'll get a firm grasp on its two key parameters, the mean and standard deviation. And third, we'll learn how to use the empirical rule. So far, with the discrete distributions, we could list all possible outcomes and their probabilities. For example, when flipping a coin 3 times, we can list the 8 possible outcomes. But what if our variable could take on any value within a range, like a person's height? This is the difference between discrete and continuous variables. With a continuous variable, we can't list all the outcomes because there are infinitely many. Think about it. Between 170 centimeters and 171 centimeters, there's 107.5, 117.51, and so on, forever. For continuous variables, we use a curve to represent the distribution, and probabilities are found by looking at the area under that curve. The most famous of these is the normal distribution. Here's what it looks like. It's often called a bell curve because of its shape. Notice it's perfectly symmetrical around its center. This central value is the most likely outcome. As we move away from the center in either direction, the curve gets lower, meaning those outcomes are less and less likely. The probability of an outcome occurring decreases dramatically as we get farther from the middle. To define any specific normal distribution, we only need 2 numbers, or parameters. The first is the mean, represented by the Greek letter mu, which tells us the center of the distribution. The second is the standard deviation, represented by sigma, which tells us how spread out the data is. A larger standard deviation means the data is more spread out, so the bell curve will be wider and flatter. A smaller standard deviation means the data is clustered tightly around the mean, so the curve will be taller and narrower. We use this shorthand notation to say that a random variable x follows a normal distribution with a mean of mu and a variance of sigma squared. Remember, variance is just the standard deviation squared. This distribution is incredibly common in the real world. Many things naturally follow this pattern. For instance, people's heights and weights, scores on standardized tests like the IQ test, and even the precise mass of products coming off a production line tend to be normally distributed. So to recap, the normal distribution is a symmetric, bell-shaped curve for continuous data, defined by its mean and standard deviation. Now let's see what we can do with that. Now that we know the shape of the normal distribution, let's explore a very powerful rule that applies to every single one, regardless of its mean or standard deviation. This is called the empirical rule, or sometimes the 68-95-99.7 rule, and you'll soon see why. This rule tells us what percentage of the data we can expect to find within 1, 2, or 3 standard deviations of the mean. First, approximately 68% of all data points will fall within 1 standard deviation of the mean. That is, between the value mean minus 1 standard deviation and mean plus 1 standard deviation. So, if you pick a value at random from a normal distribution, there's a 68% chance it's in this central region. Next, if we go out to 2 standard deviations from the mean, we capture a much larger portion of the data. Approximately 95% of all values lie within 2 standard deviations of the mean. This means that values outside this range are quite rare, occurring only about 5% of the time. Finally, if we extend to 3 standard deviations from the mean, we include almost everything. Approximately 99.7% of the data lies within this range. It's extremely rare for a value to be more than 3 standard deviations away from the mean. Let's make this concrete with an example. Let's consider the weights of a population of adult men, which we'll assume are normally distributed. Suppose the mean weight, mu, is 75 kilograms, and the standard deviation, sigma, is 10 kilograms. We would write this as x follows a normal distribution with mean 75 and variance 10 squared. Now let's apply the empirical rule. Where would we expect 68% of men's weights to be? We calculate 1 standard deviation below and above the mean. That's 75 minus 10, which is 65, and 75 plus 10, which is 85. So about 68% of men in this population weigh between 65 and 85 kilograms. What about 95%? For 95%, we go 2 standard deviations out. That's 75 minus 2 times 10, which is 55, and 75 plus 2 times 10, which is 95. So 95% of the men weigh between 55 and 95 kilograms. And finally, for 99.7%, we go 3 standard deviations. That's 75 minus 30, which is 45, and 75 plus 30, which is 105. So we can be very confident that almost any man we select from this population will weigh between 45 and 105 kilograms. This rule is a fantastic tool for getting a quick feel for the data's spread without needing a calculator. It provides a solid framework for understanding what's a typical value versus what's an unusual one. All right, we've seen that the normal distribution is a powerful model, but it's not always the right one. A key skill in statistics is knowing when a particular model is appropriate. So let's ask, when is a normal distribution a good model for a set of data? There are 2 main properties we need to check for. First, the data should be continuous, or at least have many possible values. Second, the distribution of the data should be roughly symmetric. Let's create a small checklist. Is the variable continuous, and is the distribution symmetric? If the answer to both is yes, a normal model is likely a good fit. Let's look at a counterexample to see when it's not a good fit. Consider this worked example, where a sample of 20 students were asked how many siblings they have. The results are shown here in a box plot. The question asks for 2 reasons why a normal distribution would be a poor model for this data. Take a moment to think about our checklist. What's the first problem you see? The first reason is that the variable, the number of siblings, is discrete. You can have 0, 1, or 2 siblings, but you can't have 1.5 siblings. The normal distribution is fundamentally for continuous variables that can take any value in a range. Now, what about the shape of the distribution? Does it look symmetric? The second reason is that the data is not symmetric. Looking at the plot, the data seems skewed. A core property of the normal distribution is its symmetry. Since this data is not symmetric, a normal model would not represent it accurately. So because the data is discrete and not symmetric, the normal distribution is a poor model here. It's important to remember that while many things in nature are approximately normal, we can't assume it's always the case. We must always check if the assumptions fit the data. Now for the practical part. How do we calculate exact probabilities for a normal distribution? While the empirical rule gives us good estimates, we often need precise answers. For this, we'll use our calculators. Let's look at normal probability calculations. Our learning objective for this section is to use a GDC, or graphical display calculator, to find the probability that a normally distributed variable falls within a certain range. Specifically, we'll be using the normal cumulative distribution function, which is often abbreviated as normal CD or NCD on calculators. This function calculates the area under the curve between 2 points. Let's try an example. Suppose a random variable x follows a normal distribution with a mean of 10 and a variance of 25. We're given that x is distributed normally, x mod n, 10, 25. We want to find the probability that x is greater than 20. First, let's identify our parameters. What are the mean and standard deviation? The mean, mu, is 10. The notation gives us the variance sigma squared as 25. So the standard deviation sigma is the square root of 25, which is 5. This is a common trick, so always be sure you're using the standard deviation, not the variance. Now we go to our calculator's normal CD function. It will ask for a lower bound, an upper bound, the mean, and the standard deviation. Since we want the probability that x is greater than 20, our lower bound is 20. There is no upper bound, so we just put in a very large number to represent infinity, like 1 times 10 to the power of 99. Our mean is 10, and our standard deviation is 5. When we execute this, the calculator gives us the answer. The probability that x is greater than 20 is approximately 0.0228, or about 2.28%. Let's do another example, returning to the weights of men, where the mean was 75 kilograms and the standard deviation was 10 kilograms. Let's find the probability that a randomly selected man weighs between 60 and 82 kilograms. Here, our lower bound is 60 and our upper bound is 82. The mean is 75 and standard deviation is 10. Plugging this in, we get a probability of about 0.691. This means about 69.1% of men fall in this weight range. A quick but important note on inequalities. For a continuous variable, the probability of x being exactly equal to a specific value is 0. Think of it as the area of an infinitely thin line. So pxk is the same as px equal k. This is not true for discrete variables, so be careful. Let me repeat that, because it's a crucial point. For any continuous distribution, like the normal distribution, the probability of being less than a value is the same as the probability of being less than or equal to that value. The inclusion of the endpoint doesn't change the area. So, we've now seen how to use the normal CD function to find the probability of a variable falling in a specific range. This is the first major type of normal distribution problem. We've just learned how to find a probability given a value. Now we're going to flip that around. What if we know the probability and we want to find the corresponding value? This is called an inverse normal calculation. Our objective here is to find a value x on the x-axis given the area under the curve to the left or right of it. In other words, we're given the probability and need to find the boundary. For this, we use a different function on our calculators called inverse normal, often abbreviated as INVN. Let's look at an example. A trouser manufacturer wants to design sizes for adult males whose waist circumference is normally distributed with a mean of 92 centimeters and a standard deviation of 4.5 centimeters. The company wants to make sure their smallest size fits at least the bottom 5% of the population. This means they are looking for a waist size, let's call it X, where the probability of having a waist smaller than X is 0.05. So we are trying to solve the equation px then x equals 0.05. We know the probability and we want to find the value x. We turn to our calculator's inverse normal function. It will ask for the area or probability, the mean, the standard deviation, and which tail of the distribution we're interested in. Since we're looking for the smallest 5%, we are interested in the area in the left tail of the distribution. So we set the tail to left. The area is 0.05, the mean is 92, and the standard deviation is 4.5. The calculator gives us a result of approximately 84.6. This means the smallest waist size the manufacturer should offer is 84.6 centimeters to ensure they cater to all but the smallest 5% of men. Let's quickly discuss the tail setting. If the question is about less than a value, like in this case, you use the left tail. If it's about greater than a value, you use the right tail. So left corresponds to the area from negative infinity up to your value, and right corresponds to the area from your value up to positive infinity. For example, what if we wanted to find the value b such that the heaviest 4% of packs weigh more than b in our coffee example, where x to my n 515 squared? We want to find b where the probability of being greater than b is 0.04. This is a greater than problem. So we use the inverse normal function with the right tail. The area is 0.04, mean is 500, and standard deviation is 15. The calculator tells us that B is approximately 526 grams. This means the heaviest 4% of coffee packs weigh more than 526 grams. So now we have two main tools, normal CD to go from values to probabilities, and inverse normal to go from probabilities back to values. Mastering these two functions is key to solving most normal distribution problems. Let's tackle a comprehensive example that brings together everything we've learned: forward calculations, inverse calculations, and even a link back to the binomial distribution. We'll use the example about the mass of coffee packs. The problem states that the mass of a pack of coffee is normally distributed with a mean of 500 grams and a standard deviation of 15 grams. So our random variable x, the mass, follows a normal distribution with a mean of 500 and a standard deviation of 15. Part A asks for the probability that a pack weighs more than 520 grams. Is this a forward or inverse problem? It's a forward problem because we're given a value, 520 grams, and asked for a probability. We use normal CD. Using our calculator with a lower bound of 520, a very large upper bound, a mean of 500, and a standard deviation of 15, we find the probability is about 0.091, or 9.1%. Part B is an inverse problem. We're given percentages or probabilities and asked to find the corresponding weights, A and B. First, let's find A. We need to find the value A such that px 0.04. We use the inverse normal function with the left tail, an area of 0.04, and our mean and standard deviation. This gives us A is approximately 474 grams. Now for B, we need to find B such that px nu p04. This time we use the right tail with the same area of 0.04. The calculator gives us B is approximately 526 grams. The problem then states that these packs, the ones lighter than 474 grams and heavier than 526 grams, are rejected. Part C asks for the expected number of rejected packs in a batch of 1600. First, what's the total probability of a single pack being rejected? The probability of being rejected is the probability of being too light plus the probability of being too heavy. That's 0.04 plus 0.04, which equals 0.08, or 8%. The expected number is the total number of packs multiplied by the probability of rejection. So 1600 times 0.08 gives us 128 packs. We expect 128 packs to be rejected each day. Now for a tricky one. Part E asks for the probability that if we select 5 packs, at least one is rejected. This sounds familiar, doesn't it? This is a binomial distribution problem. We have a fixed number of trials, n equal 5. Each trial is selecting a pack. The outcome is either rejected, success, or not rejected, failure. The probability of success, p, is 0.08. Let's define a new variable, y, as the number of rejected packs. Y follows a binomial distribution with n equal 5 and p equals 0.08. We want to find the probability that y is greater than or equal to 1. Calculating p equals 1 plus py equals 5 is a lot of work. It's easier to use the complement. The complement of at least one rejected is none are rejected. So py might 1 is equal to 1 minus py equals 0. The probability of 0 rejections is the probability of a pack not being rejected, which is 1 minus 0.08, or 0.92, raised to the power of 5. This gives us a final answer of about 0.341. Finally, let's find the quartiles. Part F asks for the lower and upper quartiles, Q1 and Q3. Remember, Q1 is the value that separates the bottom 25% of the data, and Q3 separates the bottom 75%. These are inverse problems. For Q1, we find the value where the area to the left is 0.25. Using inverse normal, we get about 490 grams. For Q3, we find the value where the area to the left is 0.75, which gives us about 510 grams. This example really shows how different concepts can be woven together. We used our core normal distribution skills and then applied them in a binomial context. Excellent work today. Let's quickly recap our objectives. We described the properties of the normal distribution, its bell shape and symmetry. We defined it using its mean and standard deviation. We used the empirical rule for quick estimates, and we performed detailed calculations using both the normal CD and inverse normal functions on our calculators. Next time, we'll introduce a concept called standardization, which will allow us to compare different normal distributions.